After reading page 257, here are the major takeaways. Number one, stoichiometry is just a method that helps us convert and compare amounts of moles and grams and atoms and molecules or volume in a balanced equation. Now we'll focus on volume more when we get to gases. But if we had a little equation like this, nitrogen plus hydrogen forming ammonia, we're really going to focus on the ratios, which means we have to balance the equations properly. I want the coefficients or ratios from the balanced equation in order to convert between different amounts or different quantities of reactants and products. So I could read that as a ratio of 1 molecule of nitrogen reacting with 3 molecules of hydrogen, forming 2 molecules of ammonia. Or maybe on a larger scale, I would say 1 mole of nitrogen molecules plus 3 moles of hydrogen molecules, forming 2 moles of ammonia. But those ratios are amounts of particles. It's an amount of molecules or atoms. And it's just then that when I go in the lab, I'm going to multiply that by 6.02 times 10 to the 23rd so that I have a quantity that's actually measurable. Now, one way that we can kind of look at this is by graphing amounts. And so they took the same balanced equation, and the red graph shows moles of nitrogen versus moles of ammonia. So they graphed it, and if you want, you can look at the slope, the rise over run, and you should find, let's see, maybe a rise of like 16 over a run of 8. That no matter what points I pick, I'd get a slope of 2. That actually kind of matches the mole ratio in the balanced equation, that there's 1 nitrogen and 2 NH3. Again, it could be a ratio of molecules, or a larger scale, we would say moles. And I could pick a point, and I can even say, let's pick a point right in here. But yeah, for every 2 moles of nitrogen, I would produce 8 moles of ammonia. For every 10 moles of nitrogen, I would produce 20 moles of ammonia. So we don't always have to just stick to a 1-to-2 ratio. You can multiply that by whatever you want, as long as you keep the integrity of the ratio in the balanced equation. If I'm running this in our little lab, then yeah, maybe I just use a 1-to-2 mole ratio. Or maybe sometimes I would say, well, I don't really need a lot in my little lab, so I'll use half a mole of N2 nitrogen and produce 1 mole of NH3 ammonia. Totally fine, as long as I keep the integrity of that 1-to-2 ratio. I mean, on an industrial scale, this ratio would be ramped up big time, where maybe we'd have 100 moles of nitrogen producing 200 moles of ammonia, which is great. But we should always keep the integrity of that 1-to-2 ratio. Now, what they're trying to show on the blue graph is that the ratio is not a direct ratio of grams. So here they were graphing, I don't know if you caught this, that the first red graph was moles of nitrogen versus moles of ammonia. And the second blue graph is mass of nitrogen versus mass of ammonia. When I graph moles, I always got a slope of 2, which was that ratio from the balanced equation. That is not the case when I directly graph mass. That if you look rise over run, this is not a slope of 2. In fact, it's about a 1.2, which is fine. I don't need to focus on the exact ratio or the exact slope. But what I want you to get from this is that the ratio in the equation is not a direct ratio of grams or mass. Indirectly, then, yeah, like if I say, I've got 4 moles of nitrogen and it's going to produce 8 moles of ammonia, well, I can use molar mass on the periodic table to turn that into grams, but those grams then will not directly be a 1-to-2 ratio. It's it's a consistent ratio. I get a nice straight line when I graph mass, but it's not going to match the ratio from the balanced equation. And so I guess in number 8, question 8, it says, using the data from the graph, predict the mass of nitrogen needed to produce 300 grams of ammonia. So two things jump out at me here. Number 1 is that I'm supposed to use the graphs. And number 2, I'm just making a prediction. Well, eventually we'll do some calculations where we can calculate the exact mass of nitrogen needed to produce a certain mass of ammonia. And this is so real world chemistry that there's a certain amount of desired product, so I have to kind of work backwards and figure out, okay, well then how much nitrogen do I need? How much hydrogen do I need? Well, here we're just going to use the graph and make a prediction. So if I were to take this graph and I guess maybe extrapolate it out a little bit, by the time I hit 300 grams of ammonia, I don't know, it's probably like approximately, I'll say approximately 240 grams of nitrogen. I mean, it's not going to be exactly. I'm going to guess that it's, I don't know, it's probably a little bit more than that. But we'll say, like, using the graph and the data that we're given, it's probably somewhere around 240 grams. And again, that's kind of what's to come, is where we want to look at a desired product, a desired amount of product, and then work backwards to figure out, well, how much nitrogen do I need? How much hydrogen do I need? And for that, there's some fantastic calculations ahead. You're just going to love them. Now, the last question here was number 9, where they were looking at another recipe for making bread. And hopefully you're kind of catching on that we're just always obsessed with ratios, and that we don't always need to make one loaf of bread. We can just multiply these ratios times 3 and make 3 loaves of bread, right? I mean, sometimes that's why a recipe might fail. Let's say I wanted to triple a recipe. I want to make a triple batch, and I didn't triple all of my ingredients properly. But that's all I'd have to do for number 9. And that's kind of where we're going moving forward. That, I mean, sometimes we want to follow the ratio in the balanced equation exactly. I want 1 mole of nitrogen, 3 moles of hydrogen, and I want to make 2 moles of NH3 ammonia. But sometimes we might want just kind of a random amount. Like, what if I want 300 grams? Or what if I want 1,000 grams? Or maybe I want 10 grams. How can I use those ratios to get a desired amount of product? In this case, in 9, all I had to do was triple the ratios to make 3 loaves of bread.